Today's lesson is going to be a summary of our conic sections. We'll review all our different topics from where we started with to where we finished to make sure we're ready for an assessment. So we began the unit talking about the distance formula and the review from geometry. If you remember, it came from the Pythagorean theorem, and we ended up with the distance is equal to x1 minus x2 squared plus y1 minus y2 squared and you take the square root of the whole thing. So for example, if I have two coordinates, let me just plot a couple. The point 1, 1, and then the point 2, 5. If I want to find the distance between them or the length of this segment, first I'm going to plug my x coordinates into the formula. First I'm going to plug my x coordinates into the formula, which is essentially just finding this distance here. 2 minus 1 squared. And then I'll repeat for the y's, which is again just finding this distance. So we have 5 minus 1 squared. And then again, we'll take the square root of the whole thing once we've got it all figured out. So 2 minus 1 simplifies to 1. 5 minus 1 simplifies or reduces to 4. So we've got 1 squared plus 4 squared. So we're looking at the square root of 17. This is a little bit more than 4, but that's the distance between these 2 points. We used the distance formula to develop the formulas for a couple of our conic sections, but we'll come to that here in a second after we review our next topic, which is completing the square. Completing the square was a way to rearrange a quadratic expression to convert a polynomial into a perfect square. So the question was, what goes here? X squared plus 8x plus something. If I make my x square, I split my 8x evenly, so I've got 4x and 4x. If I were to complete the square, it means I have 16, so it should be x squared plus 8x plus 16. So we look for what is our general pattern if we complete this a handful of times. We're ultimately concerned with our middle term, so that's 6. We'd have to divide it by 2 and square it. So in general terms, if we have something x squared plus bx, we're going to divide our middle term by 2 and then square it. So half of 6 is 3, and 3 squared is 9, so x squared plus 6x plus 9. Similarly, with x squared minus 2x, we should still end up with a positive at the end, so it would be plus 1. And if our number is not even, we will end up with a decimal. So if we have x squared plus 7x, 7 divided by 2 is 3.5. 3.5 squared is 12.25. Now, the real reason we want to be able to do this is it turns our quadratic expression into something factorable. So x squared plus 8x plus 16 is x plus 4 squared because we have an x plus 4 on either side of our factored square. In general, it turns into x plus b over 2 squared. So the first one is x plus 3 because 6 divided by 2 is 3. Next one is x minus 1 because negative 2 divided by 2 is negative 1. And the third one is x plus 3.5 squared. Our next section is conic sections. For each shape, we have a conic definition as well as a geometric definition. So we'll go ahead and review each of those here. For a circle, we can get the shape by slicing a cone with a plane parallel to the base. The cross section is then a circle. With an ellipse, we can slice a cone with a plane that is slightly less steep or slightly more steep than the base. And for a parabola, it's the cross section when we slice a cone parallel to an edge. So each one has a geometric definition. For a circle, it's the set of all points that are a fixed distance from the center. For an ellipse, it's that fixed distance is now set between two separate points called the focus points or the foci. So here if I have D1 and D2, those two distances should add up to be the same as any other point if I were to pick any other point on the figure. So let's pick another point. Let's call this A1 and A2. What this means is that A1 plus A2 should be the exact same. It should be equal to D1 plus D2. And this is true for any point on the ellipse. Those two distances are fixed. For a parabola, it's the set of all points that are equidistant from a line called the directrix and a point called the focus. So these 2 points, or this point is the same distance from the focus as it is the directrix. However, that distance is not the same everywhere, but it is always the same distance from the directrix to the focus. Right? Each pair of distances is the same. So these have been our geometric and conic definitions of each shape. We also looked at the equations of each shape and how to use those, or how to graph them. So we'll go through one at a time. We'll start with circles. The equation of a circle should always look something like x minus h squared plus y minus k squared equals r squared, where r is the radius. So I'm going to draw an x and y axis here. Let's suppose I want the center of my circle to be at 2, 4, and it has a radius of 2. So what I can do is I can just plug each number into the equation. We get x minus 2 squared plus y minus 4 squared from the center, and that equals 2 squared because 2 is our radius. And that's the equation of this circle. We should also be able to work in reverse. We should also be able to read an equation for a circle and tell where its center and radii are. Now, sometimes this might involve completing the square. So here is the equation of a circle, x squared plus 6x plus y squared minus 14y plus 33 is equal to 0. So what we need to do is we need to complete the square for x, we need to complete the square for y, and then we just need to move all of the extra numbers over to the edge. So if I look at the x minus h squared, I've got x squared plus 6x. Doing exactly what we did earlier, we would have x squared plus 6x plus 9. And now I'm going to repeat this for the y. Since I added 9 over here, I have to add 9 to the other side to keep everything equal. So I'm going to repeat that process for the y. I've got y squared minus 14y. 14 over 2 is 7. 7 squared is 49. So I'm going to add 49 right here. So I have to add 49 to the other side as well. And now that plus 33, I'm just going to subtract that here. I'll subtract that over there. Right? There's no extra numbers on the left-hand side if we look at the standard form. So all told, On the left-hand side, x squared plus 6x plus 9 turns into x plus 3 squared. Y minus 14 squared plus 49, or y squared minus 14y plus 49 turns into y minus 7 squared. And 9 plus 49 is 58. 58 minus 33 is 25. So we have x plus 3 squared plus y minus 7 squared equals 25. So here's what that tells us about our circle. It's got a center at -3, 7. And it's got a radius of 5. So now let's sketch this circle, just so we can make sure we know what it looks like. So it's got its center at -3, 7, which is right here, and its radius is 5. So we go up, down, left, and right, 5. Plot our edge coordinates. And luckily, with some digital assistance, I will graph the circle. Next up is the ellipse. So the ellipse is similar to a circle. It's really just a stretched out circle. Rather than having one radius, we have a major axis and a minor axis. So like we did with the circle, we'll go look at the standard form of the equation, which is x minus h squared over a squared plus y minus k squared over b squared is equal to 1. So we'll graph a circle, or an ellipse rather. We'll graph an ellipse. So we'll graph an ellipse, and then we'll identify all of the parts. So this a squared is our radius in the x direction, and this b squared is the radius in the y direction. And now to find where those two focal points are, they are c units away from our center. And it's always along the major axis. And we can find c using the equation c squared equals a squared minus b squared. So we'll look at the equation of an ellipse, we'll graph it, we'll identify all of the parts. So let's consider x minus 3 squared over 9 plus y plus 1 squared over 16, or over 25, is equal to 1. Now we should be able to read the equation and identify a few key features. First, the center is at the point 3, -1. Because 25 is larger than 9, it's oriented vertically. And then we'll take the square root of our 9 and our 25, and that tells us our kind of our up and down radii, if you will. So we're going to go up and down 5. We're going to go left and right 3 from the center. And that will give us the edges of our ellipse. So I'll start by plotting the point 3, -1. Now if I go up and down 5, these are the vertices, or the vertex points. The vertex points are always the ends of the major axis. Our major axis is vertical. So now we'll go left and right 3. These are our co-vertices, our co-vertex points. Those are always the ends of the minor axis. So now we can sketch our ellipse. Let me try again. Good enough. This is roughly our ellipse. Now I do want to know where the focus points are, so I can graph those as well. So those are going to be c units up and down from our center. So I'll use the equation c squared equals a squared minus b squared. A squared will always be the larger one, 25. B squared will always just put in the smaller one. That way it stays positive. 25 minus 9 is 16. So C is equal to the square root of 16, which is 4. So that means our two focus points are up and down 4 from the center of the ellipse. The two focus points should always be inside and on the major axis. So our focus points are at 3, 3, and 3, negative 5, right? Up and down 4 from the center. Finally, we have the parabola. So the parabola, which we've studied before in Algebra 2, gives us that nice U shape. Now, the two important features we do need to make sure we add to our parabolas now are the focus and the directrix. So we'll call our vertex here at the point HK. Now here's that line, the directrix, that I mentioned in the geometric definition. It should always be outside of the parabola. And it is always P units away. That's going to come in handy when we write the equation. Now equidistant on the other side, also P units away, is the focus. So the equation of this parabola is x minus h squared equals 4p y minus k. H and k is still the center, or the vertex, and p is the distance from the focus to the vertex. If x is squared, the parabola if x is squared, the parabola will open up or down. If 4p is positive, it will open up. If 4p is negative, it will open down. If y is our squared term, however, then we get a parabola that opens to the left or to the right. So just a rough sketch. Here's a parabola that opens to the right. We still call our center HK. Here we have our directrix. And then our focus, they are still P units away, or we still call that distance P. So this parabola is y minus k squared equals 4p x minus h. So let's take a look at an example of one, try to write the equation and identify it. Or look at the equation and try to sketch the graph. So here we've got y minus 2 squared equals 6 x plus 1. So a couple of things to note. First, our vertex, or first this opens to the right. Because y is our squared term, it's going to open either left or right, and because 6 is positive, it opens right. The vertex is at the coordinate -1, 2, and then if 4p is 6, then p is 1.5. So that tells us our distance from the vertex to the directrix and vertex to the focus. So we'll sketch it first by graphing the vertex at -1, 2. Now the p is 1.5, which means if I go 1.5 units to the left, that'll give me the directrix. So that is a vertical line right here. And if I go 1.5 units to the right, that gives me the focus. Now, if we want to be a little more careful with our sketch, we'll need to use the focal width. Our focal width being 4p, so it's 6. That just means at the focus, it should be 6 units wide. So I'll go up 3 and down 3. Give me a couple of other points on the parabola. And there we go. Just a good sketch. Should look like a satellite dish. This has been Conic Sections.